Water vital for human life. Humans need water for dissolution of nutrients like vitamins, amino acids, mineral substance and others. Water important for supplying all cells of the body with nutrients. We need water for removing decay products and toxins from the body, water maintaining body temperature, water important for supporting motor activity and transporting nerve impulses throughout the body. Providing the population with good quality drinking water, safe in terms of epidemics and harmless in terms of chemical composition, is an important condition for preventing diseases and directly contributes to achieving good health and well-being. There are two types of the water supply system, centralized and decentralized. What means water supply? Water supply is a system of organizing the provision of water to the population, industrial, agriculture, and other facilities for various needs. It includes the processes of water abstraction, purification, transportation, and delivery to consumers. Depending on the water sources, water supply can be by centralized water system and decentralized. Centralized water system means a system of pipes or other distribution devices designed to distribute potable water from a treatment facilities to residential or commercial premises. The sources can be rivers, lakes, reservoirs, or wells. Decentralized water system use of local water sources like wells, artesian wells, local water intake facilities. Centralized water system use large plants and extensive pipes for big areas, offering economies of scale but high infrastructure cost and vulnerability. Decentralized system use smaller local treatment units like point-of-use filters or small community plants near the user, providing flexibility, resilience, lower setup cost, and tailored solution, but require more user involvement for maintenance. Centralized is efficient for large cities, while decentralized excels in remote areas, offer disaster resilience with modern trend, favoring decentralization for adaptability. Centralized or other name public water system or community water system serve millions of households around the world. However, this system do often not reach the poorest or the most remote populations, and quality and quantity of water provided are often unreliable due to poor operation and maintenance. Decentralized or private water system offer the possibility to provide safe drinking water where centralized supply systems are not feasible due to technical, economical, or institutional reasons. For example, in rural communities or informal settlements. Decentralized water supply refers to the small-scale purifications and distribution of water. What about centralized water system? How it works? A single large treatment plant collects water, purifies it, and distributes it via a vast network of pipes to a large population. There are some advantages of centralized water system. Economies of scale, that means lower cost per volume once built. Consistent quality across a large service area. But also there are some disadvantages like high initial capital cost, vulnerability to single point failures, potential for leaks and contamination in long pipe network, less adaptable to local needs. best for densely populated urban areas where large investments are feasible. What about decentralized water system? How it works? Smaller, localized treatment units like point of entry, point of use or small community plants treat water close to where it's needed. Advantages of decentralized water system: lower initial cost, increased resilience, one unit failing doesn't affect the whole system, flexibility, suitability for remote areas, reduces needs for extensive piping, enables local reuse. Also, there are some disadvantages of decentralized water system. Can require more day-to-day operations by users, like filter changes, capacity limitation compared to hug plants, requires managing multiple small system. Best for rural areas, remote communities, disaster relief, industrial sites, or as a supplement to existing centralized system. Key components of centralized drinking water system. First of all, we should choose water sources. Like water sources, we can use surface water, lakes, rivers, reservoirs, groundwater, wells or aquifers, and desalinated water, seawater treated through desalination. On the slide you can see two main types of water sources: surface water and groundwater. Surface water refers to bodies of water that provide water to public drinking water supplies and private wells. These bodies of water can include rivers, streams, lakes, reservoirs, springs, and water under the ground. Groundwater is located below the surface of the earth in spaces between rock and soil. Surface water collects on the ground or in a stream, river, lake, reservoir, or ocean. Surface water and groundwater are both important sources for community water supply needs. Groundwater is a common source for single homes and small towns, and rivers and lakes are the usual sources for large cities. Also, approximately 98% of liquid fresh water exists as groundwater, much of it occurs very deep. This makes pumping very expensive, preventing the full development and use of all groundwater resources. All surface water sources are subject to continuous or intermittent pollution and must be treated to make them safe to drink. One never knows when the organism causing diseases such as typhoid fever, gastroenteritis, giardiasis, or infection hepatitis A will contaminate surface water sources. The extent of the treatment required will depend on the result of a sanitary survey made by an experienced professional, including physical, chemical, and microbiological analysis. Protecting surface water from pollution is difficult because, as noted earlier, the activities of upstream users of the river water will affect the quality of the water for downstream users, and the land use in the surrounding areas will also have an impact. Surface water are by definition unprotected sources. Water has much a strong tendency to dissolve other substances that it is rarely found in nature in a poor condition. When it falls as rain, small amount of gases such as oxygen and carbon dioxide become dissolved in it. Raindrops also carry tiny dust particles and other substances. As it flows over the ground, water picks up fine soil particles, microbes, organic material, and soluble minerals. In lakes, bogs, and swamps, water may gain color, taste, and odor from decaying vegetation and other natural organic matter. On this slide you can see how local river or lake where presents different pollution. Groundwater usually acquires more dissolved minerals that does surface runoff because of its long direct contact with the soil and rocks. It may also absorb gases such as hydrogen sulfide and methane. In polluted areas, the quality of surface water as well as groundwater is directly influenced by land use and by human activities. For example, storm water runoff contaminated with agricultural or lawn pesticides and fertilizers, as well as with road icing chemicals or motor oils can flow into streams and lakes. In addition, effluent from malfunctioning septic tanks and subsurface leaching fields can seep into groundwater. Key differences: scale and location. Centralized, large distance, or decentralized, small local. Infrastructure: centralized need massive pipe network, decentralized minimizes piping. Positive or advantages of centralized or disadvantages of centralized has high upfront cost. Decentralized has lower setup but potentially higher ongoing management. Resilience: decentralized is more resilient to large-scale disruptions. Groundwater in centralized drinking water system. Many cities and towns rely on groundwater for their drinking water supply. Centralized system extract, treat, and distribute it to consumers. Key steps in using groundwater for drinking water. Groundwater is pumped to the surface using deep well or boreholes. For groundwater should be used different method of water treatment. Here you can see a list of different treatments methods, various based on the groundwater quality. Some groundwater need filtration for removes sediments and particles. Another groundwater need aeration for eliminates dissolved gases like hydrogen sulfide. Another water can need softening, which can reduce hardness caused by minerals like calcium and magnesium. All groundwater need disinfections, which can kill bacteria and viruses by different methods with the help of chlorine, ultraviolet, or ozone. Sometimes some water need to remove arsenic, nitrates, or fluoride if presence is excess amount. Storage and distribution for groundwater are next. Treated water is storage in special reservoirs or tanks and distributed through pipelines. Advantages of using groundwater: usually clean than surface water, due to the result protected from direct pollution, less affected by seasonal varieties. Groundwater requires less treatment compared to surface water, and groundwater naturally filtrated through soil and rocks. But also there are some challenges and risks for groundwater. Over extraction can deplete aquifers. Contamination from human activity For example, industrial waste, pesticides, septic system also can be in groundwater. Salinity and hardness issues in some areas can be very high. And groundwater slow reaches rate, making it a finite resource if not managed properly. Before fresh water can be considered potable, it must be treated to be made safe for drinking. Municipal water supply systems include facilities for storage, transmission, treatment, and distribution. The design of these facilities depends on the quality of the water, on the particular needs of the user or consumer, and on the quantities of water that must be processed. Key components of centralized drinking water system are next. For water treatment, use next methods: coagulation and flocculation, which help to remove large particles; sedimentation, which helps settle heavy particles; filtration removes small contamination; and disinfection kills bacteria and viruses with the help of chlorination or ultraviolet treatment. On this scheme you can see all these main steps for water treatment. Advantages of centralized water system are next: consistent water quality, compliance with health and safety standards, efficient large-scale distribution, better control and monitoring, regular water quality testing, lower long-term cost per household. Challenges of centralized water system are high initial infrastructure cost, maintenance and contamination risk, dependence on a single sources which may be vulnerable to droughts or pollution. We always should remember about drinking water quality. Water quality standards set limits on the concentration of impurities allowed in water. Standards also affect the selection of raw water sources and the choice of treatment processes. All water which drink people should correspond to special water quality standards. Water in rivers or lakes is rarely clean enough for human consumption if it is not first treated or purified. Groundwater, too, often needs some level of treatment to render it potable. The primary objective of water treatment is to protect the health of the community. Potable water must, of course, be free of harmful microorganisms and chemicals, but public supplies should also be aesthetically desirable so that consumers will not be tempted to use water from another, more attractive but unprotected sources. The water should be crystal clear, with almost no turbidity, and it should be free of objectionable color, odor, and taste. For domestic supplies, water should not be corrosive, nor should it deposit troublesome amount of scale and stains on plumbing fixtures. Industrial requirements may be even more stringent. Many industries provide special treatment on their own premises. The type and extent of treatment required to obtain potable water depends on the quality of the sources. The better the quality, the less treatment is needed. Surface water usually needs more extensive treatment than does groundwater, because most streams, rivers, and lakes are polluted to some extent. Even in areas remote from human populations, surface water contains suspended silt, organic materials, decaying vegetation, and microbes from animal wastes. Groundwater, on the other hand, is usually free of microbes and suspended solid because of natural filtration as the water moves through soil. Though it often contains relatively high concentration of dissolved minerals from its direct contact with soil and rock. Water is treated in a variety of physical and chemical methods. Treatment of surface water begins with the intake screens to prevent fish and debris from entering the plant and damaging pumps and other components. On this scheme you can see that first step for water treatment begins from the intake screen. Conventional treatments of water primarily involves clarification and disinfection. Clarification removes most of the turbidity, making the water crystal clean. And also on the scheme you can see that clarification begins from coagulants added. In water should be add coagulants for begin process of coagulation. After add coagulants, water should be flush mix tank. In this tank begin process of sedimentation. After sedimentation should be used process which name filtration through special rapid dual media filter or maybe another filter used for water filtration. Disinfection, usually the final steps in the treatment of drinking water, destroys pathogenic microbes. And on the scheme you also can see how after clarification, after filtration, in water which look like clear water, add special disinfectant. In this case here is chlorine solution. Groundwater does not often need clarification. Now you understand why, because groundwater don't have turbidity, don't have any particles and look nice because transparent and not color, not smell presence in this water. But groundwater should be disinfected as a precaution to protect public health. Disinfection is process which need any water from any sources. In addition to clarification and disinfection, the process of softening, aeration, carbon absorption and fluoridation may be used for certain public water sources. Not always, only some water need this additional process. Little late I explain when and why. Desalination processes are used in areas where fresh water supplies are not readily available. Here you can see how look water from the river or lake. Water is not transparent. That means water have high turbidity. What is turbidity? Turbidity refers to cloudiness caused by very small particles of silt, clay, and other substances suspended in water. Even a slight degree of turbidity in water is objectionable to most people. Turbidity also interferes for disinfection by creating a possible shields for pathogenic organisms. Groundwater normally has very low turbidity because of the natural filtration that occurs as it percolates through the soil. Surface water throws are often high in turbidity. Coagulation is often the first steps in water treatment. Treatment plants, staff, add chemicals to the water that help bind together dirt and other small particles. The chemicals they commonly use include specific types of salt, aluminium or iron. Flocculation is next. Flocculation is the gently mixing of the water to form larger, heavier particles called floc. Often treatment plant staff will add additional chemicals during this step to help the flocks form. These chemicals named flocculants. Coagulation and flocculation. Suspended particles cannot be removed completely by plain settlings. Large, heavy particles settle out readily, but smaller and lighter particles settle very slowly, or in some cases do not settle at all. Because of this, the sedimentation step is usually preceded by a chemical process known as coagulation. Chemicals, as the name coagulants, are added to the water to bring the settling particles together into larger, heavier masses of solid called floc. Aluminium sulfate, another name alum, is the most common coagulant used for water purification. Other chemicals such as ferric sulfates or sodium aluminate may also be used. In this slide you can see a scheme of coagulation process when in the water with different impurities add coagulants. After that, in second glass you can see process of coagulation and sedimentation. Coagulant absorbed onto impurities, and in last glass flocs are formed and settled. Same processes you can see in the glass with water. Sedimentation separates out solid from the water. Flocs are heavier than water, so they settle to the bottom of the water during this step. Filtration is the next step. Once the flocs have settled to the bottom of the water, the clear water on top goes through several filters. For filtration, took only a top part of this step, clean. Filtration. Even after coagulation and flocculation, sedimentation does not remove enough suspended impurities from water to make it crystal clear. The remaining non-settling flocs causes noticeable turbidity in the water and can shield microbes from disinfection. Filtration is a physical process that removes these impurities from water by percolating it downward through a layer or bed of porous granular material such as sand. Suspended particles become trapped within the pore space of the filter media, which also remove harmful protozoal and natural color. Most surface water supplies require filtration after the coagulation and sedimentation steps. For surface water with low turbidity and color, however, a process of direct filtration which not preceded by sedimentation may be used. On this slide you can see scheme of some sand filter which used for water filtration. Two types of sand filter are in the use: slow and rapid. Slow filters require much more surface area than rapid filters and are difficult to clean. Most modern water treatment plants now use rapid dual media filters following coagulation and sedimentation. But now on the scheme you can see, on the slide you can see scheme of slow sand filter, which consists from the layer of the stone, next layer gravel, and next layer sand, which help to filtration of water through these three layers, but additional in sometimes on the upper surface of the sand can forming biological layer. And another name of slow sand filter are biological filter. But slow sand filters have a number of unequal qualities. Unlike other filtration methods, slow sand filters use biological processes to clean the water and a non-pressured system. Slow sand filters do not require chemicals or electricity to operate. Cleaning is traditionally done by use of a mechanical scraper, which is usually driven into the filter bed once the bed has been dried out. However, some slow sand filter operators use a method called wet harrowing, where the sand is scraped while still underwater and the water used for cleaning is dried to waste. For municipal system, there usually is a certain degree of redundancy since it is desirable for the mixing requires throughput of water to be achievable with one or more beds out of service. Slow sand filters require relatively low turbidity levels to operate efficiently. In summer conditions with high microbial activity and in conditions where the raw water is turbid, blinding of the filters due to bioclogging occur more quickly and pre-treatments is recommended. Unlike other water filtration technologies that produce water on demand, slow sand filters produce water at a slow, constant flow rate and are usually used in conjunction with a storage tank for peak usage. This slow rate is necessary for healthy development of the biological processes in the filter. Due to the low filtration rate, slow sand filters require extensive land area for a large municipal system. Many municipal systems in the Ukraine initially used slow sand filters, but as cities has grown and because of their needs for treat high turbidity sources of water, they subsequently installed rapid sand filters due to increased demand for drinking water. The rapid sand filter or rapid gravity filters is a type of filter used in water purification and is commonly used in municipal drinking water facilities as part of the multiple-stage treatment system. These systems are complex and expensive to operate and maintain and therefore less suitable for small communities and developing nations. A rapid sand filter is a key component in municipal water treatment. Using layers of sand and gravel to quickly remove suspended particles and turbidity from water, but it needs pre-treatment like coagulation, flocculation, and post-treatment disinfection to produce safe drinking water. This system operates at high filtration rates, require frequent cleaning by backwashing, another method of cleaning in opposite to previous filter, which named backwashing, and are ideal for large-scale treatment where land is limited and resources for operating are available. Here you can see scheme of rapid sand filter. The most important microbiological measure of drinking water quality is a group of bacteria called coliforms. Coliform bacteria normally are not pathogenic, but they are always present in the intestinal tract of humans and are excreted in very large numbers with human waste. For remove bacteria from the drinking water should be used method which named disinfection. Disinfection destroys pathogenic bacteria and is essential to prevent the spread of waterborne disease. Typically, the final process in drinking water treatment it is accomplished by applying either chlorine or chlorine compounds, ozone or ultraviolet radiation to clarified water. Short about chlorination. The addition of chlorine or chlorine compounds to drinking water is called chlorination. Chlorine compounds may be applied in liquid and solid forms for instance liquid sodium hypochlorites or calcium hypochlorites in tablets or granular forms. However, the direct application of gaseous chlorine from pressurized steel containers is usually the most economical method for disinfecting large volumes of water. Benefits of chlorination. Effective against most pathogens. Cost effective and easy to implement. Provides residual protection against recontaminations. Enhanced test and odor control when used properly. But there are some challenges and risks for water chlorination. Chlorination can produce disinfection byproducts like trihalomethanes, which may pose health risks. Chlorination requires careful dosage control to avoid excessive chlorine levels. Chlorination ineffective against some protozoa like Cryptosporidium, and chlorination can cause chlorine strong taste and odor can be unpleasant. Another method of water disinfection use ozone, or name of this method ozonization. Ozone gas may be used for disinfection of drinking water. However, since ozone is unstable, it cannot be stored and must be produced on site, making the process more expensive than chlorination. Ozone has the advantages of not causing taste or odor problems. It leaves no residual in the disinfected water. The lack of the ozone residual, however, makes it difficult to monitor its continued effectiveness as water flows through the distribution system. Another method of water disinfection: use ultraviolet rays. Ultraviolet radiation destroys pathogens, and its use as a disinfecting agent eliminates the need to handle chemicals. It leaves no residual and it does not cause taste or odor problems, but the high cost of its applications make it a poor competition with either chlorine or ozone as a disinfectant. The processes of disinfecting drinking water needs to take into account a number of variables such as efficiency, cost, environmental impact, and utility. It is cheaper and common, but it is limited in ways that warrant trying another process. On the slide you can see a special scheme which show for you cost comparisons of drinking water treatment methods. Which method more cheaper and which method is more expensive. Additional treatment. Additional treatment used for some water which have some additional or purification or need some additional purification or have some contamination which needs this additional treatment. Begin from the color, taste and odor. Color, taste and odor are physical characteristics of drinking water that are important for aesthetic reasons rather than the health reason. Color in water may be caused by decaying leaves or by algae, giving it a brownish yellow hue. Taste and odor may be caused by naturally occurring dissolved organic or gases. Some well water supplies, for example, have a rotten eggs odor that is caused by hydrogen sulfide gas. Chemical impurities associated with the aesthetic quality of drinking water include iron, manganese, copper, zinc and chloride, which can change or water color or water taste. Dissolved metals impair a bitter taste to water and may stain laundry and plumbing fixtures. Excessive chlorides give the water an objectionable salty taste. for remove color test or transparent odor of the water should be used some method. No, first of all, method named aeration. Aeration is a physical treatment process used for test and odor control and for removal of dissolved iron and manganese. It consists of spraying water into the air or cascading it downward through stacks of perforated trays. Dissolved gases that cause taste and odor are transferred from the water to the air. Oxygen from the air meanwhile reacts with any iron and manganese in the water, forming a precipitate that is removed by sedimentation and filtration. And carbon absorption, an effective method for removing dissolved organic substances that cause taste, odor, or colors is absorption by activated carbon. Adsorption is the capacity of a solid particles to attract molecules to its surface. Powdered carbon mixed with water can absorb and hold many different organic impurities. When the carbon is saturated with impurities, it is cleaned or reactivated by heating to a high temperature in a special furnace. Another parameter of water quality is hardness. This is a term used to describe the effect of dissolved minerals, mostly calcium and magnesium. Minerals cause deposits of scale in hot water pipes, and they also interfere with the lathering action of soap. Hard water does not harm human health, but the economic problems it causes make it objectionable to most people. Here you can see how look hard water in the heater system. For remove water hardness should be used process special treatment methods which name water softening. Softening is the process of removing the dissolved calcium and magnesium salts that cause hardness in water. It is achieved either by adding chemicals that form insoluble precipitation or by ion exchange. Chemicals used for softening include calcium hypoxide, slaked lime, and sodium carbonate soda ash. The lime soda methods of water softening must be followed by sedimentation and filtration in order to remove the precipitation. Ion exchange is accomplished by passing the water through columns of a natural or synthetic resin that trades sodium ions for calcium and magnesium ions. Ion exchange columns must eventually be regenerated by washing with the sodium chloride solution. Fluoridation. This method used when in water less amount of fluorine. Many communities reduce the incidence of tooth decay in young children by adding sodium fluoride or other fluorine compounds to filtrated water. The dosage of fluoride must be carefully controlled. Low concentrations are beneficial and cause no harmful side effect, but very high concentration of fluoride may cause discoloration of tooth enamel. But on the first slide you can see how look tooth decay due to the low fluoride in the drinking water. The fluoridation, in opposite to fluoridation, is a downward adjustment of the level of fluoride in drinking water. Worldwide, fluoride is one of the most abundant ions present in groundwater. The defluoridation process is based on the principle of electrolysis using aluminium plate electrodes placed in the raw water containing excess fluoride. During the electrolysis, Another gets ionized and fluoride is removed by complex formation, absorption, precipitation, coagulation and settling. On the second photo you can see how look teeth with teeth of the person who drink water with high level of fluoride. This problem named dental fluorosis. Desalination or desalting is the separation of fresh water from salt water or brackish water. Major advances in desalination technology have taken place since 1950s as the need of supplies of fresh water has grown in arid and densely populated areas of the world. Desalted water is the main sources of municipal supplies in areas of the Caribbean, the Middle East, the North Africa, and its use is increasing in the southeastern United States. Also, it is relatively expensive to produce. Desalted water can be more economical than the alternative of transporting large quantities of fresh water over long distance. There are two basic types of desalting technologies: thermal processes and membrane processes. Both types consume considerable amounts of energy. Thermal methods involve heat transfer and a phase change of water from liquid into vapor or ice. Membrane methods use very thin sheets of special plastic that act as selective barriers, allowing pure water to be separated from the salt. Thermal process. Distillation, a thermal process that includes heating, evaporation, and condensation, is the oldest and most widely used of desalination technologies. Modern methods for the distillation of large quantities of salt water rely on the fact that the boiling temperature of water is lowered as air pressure drops, significantly reduce the amount of energy needed to vaporize the water. On the scheme you can see how look processes of evaporation and condensation of water during desalination. Systems that utilize this principle include multi-stage flash distillation, multi-effect distillation, and vapor compression distillation. In the down of this slide you can see scheme of reserve osmosis, which also help to remove different ions, different salt from the water and make fresh water. Now we will talking about water sources for private system, or another name, decentralized water supply system. If people do not get water from a public water system, they most likely have a private groundwater well. Groundwater is naturally filtrated, which might remove some germs and chemicals. How much is filtrated out depends on how far the water is below ground and the area's local geology. Groundwater is water storage beneath the Earth's surface in aquifers, natural underground reservoirs to permeable rocks or soil that hold and transmit water. It is accessed through wells and springs and serves as a major source of drinking water worldwide. Well water is generally very safe, and the minerals present make for healthy and tasty water. Typically, groundwater is naturally clean and safe to drink. Because the soil on top acts as a filter, groundwater is usually free of microorganisms that may cause disease. However, groundwater can become contaminated if the casings or caps for well are not installed in the correct way. Groundwater may or may not be a safe water sources. In fact, there is considerable uncertainty with groundwater in different hydrogeological contexts. The widespread presence of contaminants such as arsenic, fluoride, and salinity can reduce the suitability of groundwater as drinking water sources. Arsenic and fluoride have been considered a priority contaminants at the global levels. Also, priority chemicals will vary by country. A well is a hole drilled into the ground to access water contained in an aquifer. A pipe and a pump are used to pull water out of the ground, and a screen filters out unwanted particles that could clog the pipes. Wells come in different shapes and size depending on the type of materials and wells is drilled into and how much water is being pumped out. There are three types of private drinking water wells: ducts or bored wells, driven wells, and drilled wells. Duct wells. Duct wells, also known as shallow wells, are one of the most straightforward and commonly used types of water wells. These wells are manually dug into the ground until they reach the water table, which is typically found within 25 feet. Duct wells are often lined with bricks, stones, or concrete walls to prevent collapse. While these wells are relatively easy to construct and maintain, they are more susceptible to contamination from surface water, making regular testing and treatment essential. Driven wells are similar to duct wells in terms of the depth, but are constructed differently. Instead of manual diggings, driven wells are created by using a pipe or casing that is forcefully driven into the ground using a heavy hammer or machine. The water is extracted through a shallow well pump installed within the casing. Driven wells are cost effective and can provide access to water within 30 feet. However, they are also vulnerable to contamination and may require continuous monitoring and maintenance. Dry point wells, also known as sand point or well point wells, are a cost-effective options for shallow water sources. These wells are constructed with small diameter pipes with a screened tip that is driven into the ground through the use of driving tools. Driven points wells are suitable for accessing water within 25 feet and are commonly used for household purposes such as lawn irrigation or non-potable water. However, they may be more prone to contamination and require regular monitoring and maintenance. And third types of the wells named dry-let wells. Dry-let wells are typically deeper and offer a more reliable sources of water. These wells are created using drilling rigs that can penetrate various types of soil and rock formation. Dry-let wells can reach depth of 100 or even thousands of feet, providing access to water from deep underground aquifers. Due to their depth, dry-let wells are less prone to contamination, making them a safer option for a clean water supply. However, the drilling process is more complex and can require specialized equipment and professional expertise. Protection of well water from pollution and contamination is very important information. Before and during water sources development, Care should be taken to minimize possible risk. The well should be located on a higher level than possible sources of contaminants such as latrines and septics, a pit for collection of waste matter and water, especially sewage. This is because the liquid from the pit may seep into the surrounding ground and into the groundwater. If the latrine is higher up a slope than the well, then the contaminated groundwater is likely to flow downwards and into the well. In normal soil, the minimum distance between the well and the sources of contaminants should never be less than 15 meters, and a distance of 35 meters is recommended. However, for limestones and some other soil formation, this distance needs to be greater because groundwater can pass very easily through some rocks and soils. The inside wall of the well should be made waterproof by constructing a well casing. As noted above, in smaller diameter bored wells the casing can be a pipe, but in larger wells the casing needs to be constructed by cementing from the top of the well down to a minimum depth of 3 meters. The casing of the well should also be extended for a minimum of 60 centimeters above the surrounding ground level to prevent the entrance of surface runoff. A concrete cover should be fitted over the casing to prevent dust, insects, small animals, and any other contaminants. On this slide you can see main equipments of the sanitary well, water well construction. You can see that any well must have waterproof walls. Any wells must need special clay log around the well, or any nice well must have special buckets for take water from this well. A pump should be installed, but if a pump is not available, then a sanitary bucket and rope system may be used. The immediate area of the well should preferably to fenced to keep animals away. The area surrounding the well should be graded off. It should stop away from the well in order to prevent the flow of storm water into the well. There are many potential sources of well water contaminations. Natural sources include minerals in the soil or rocks the well is drilled into, as well as runoff from agricultural feeds or animal manure. In addition, man-made contamination can come from septic tank leaks, stormwater runoff, or leaking underground storage tank. There are several other potential causes of well water contamination. Some of the most common causes include bacteria, chemicals, minerals, and radiation. What about bacteria? Bacteria are the most common cause of well water contamination. Bacteria can enter the water supply through contaminated rainwater, sewage, or agricultural runoff. Chemicals can enter the water supply through industrial waste, agriculture, or even household cleaning products. Minerals can enter the water supply through naturally occurring sources such as rocks and soil. Radiation can enter the water supply through various sources such as nuclear power plants or radioactive waste. Well, water contamination can have several harmful effects on human health. Some common contaminants such as lead and bacteria can cause serious health problems if ingested. Others such as nitrates and pesticides can also be harmful if present in high levels. The symptoms of well water contamination can vary depending on the type of contaminant present. Contaminated well water can cause a variety of health problems ranging from mild gastrointestinal distress to more serious issues like liver or kidney damage. Some other common symptoms include skin irritation, flu, or more serious issues like neurological damage and cancer. Private wells are not regulated. Tap water from private well is not regulated, treated, or monitored by officials. The regulations that protect public drinking water system do not apply to privately owned wells. Therefore, you are responsible for making sure your private well water is safe to drink. There are some steps to keep your well water safe. You should remember that proper well construction and continued maintenance help keep your well water safe. Locate your well a safe distance from possible sources of harmful germs and chemicals. Make sure your well is at least 50 feet from septic tanks, from septic leach fields, from livestock yard. Make sure your well is at the least 100 feet from petroleum tanks, from where liquid tight manner is stored, and from where fertilizer is stored or handled. And make sure your well is at least 250 feet from manure stacks. 1 foot is equal to 30.48 centimeters. That means 50 feet is near 15.24 meters. Advantages of the well. Well have next advantages. Financial benefits. No water bills. After the initial installation cost, you eliminate monthly water usage fees, paying only the electricity to run the pumps. And long-term savings. The upfront investments can pay for itself over time through reduced utility cost. Second advantages of the well. Quality and health benefits. Water is naturally filtrated through soil and rocks, removing some impurities. This water, rich in minerals, contains healthy minerals like calcium and magnesium, often lacking in treated city water, enhancing taste and health. To these advantages also belong that untreated by harsh chemicals like chlorine or fluoride, leading to a fresher taste. In this water absent any chlorine or other additives. Third advantages of well water: independence and reliability. Not affected by municipal water bans or service interruption during natural disaster. And you can control your own water sources and usage, offering peace of mind. Fourth advantages of the well water: environmental and property value. Well water is eco-friendly, uses less energy than large-scale municipal treatment plants, and increased property value. A private well can make a home more appealing and valuable to buyers seek self-sufficiency. Well water main disadvantages include high upfront cost, complete homeowner responsibility for testing and maintenance, vulnerability to power outages affecting the pump, potential contamination from bacteria, nitrates, or heavy metals can be present, requiring ongoing cost for filters or treatment system, and plus the inconvenience of hard water issues. I want to again repeat about common well water contamination. Here are a few contaminants that are most commonly found in well water. First of all, here is heavy metals. Arsenic, copper, chromium, and lead are just a few of the heavy metals that can get into your well water supply via the movements of groundwater, surface water, seepage, and runoff. These contaminants wreak havoc on a range of vital organs such as the liver, kidney, and intestines. These metals can also cause cancer. Pesticides and herbicides. Due to their widespread use in agriculture and industry, pesticides and herbicides end up in well water supplies because of runoff, waste disposal, and spills. These contaminants can cause damage to the kidney and liver as well as the circulatory, nervous, and reproductive system. Nitrate and nitrates. These contaminants come from chemical fertilizers, human sewage, and animal waste, and they end up in your well water supply because of groundwater movements, surface water seepage, and after runoff. Microorganisms. Contaminants like bacteria, viruses, and parasites can all find their way into your water supply through runoff from rain or snow melting and leakage from underground storage tanks and septic leach fields. These contaminants can cause gastrointestinal illnesses and infection when ingested. And fluoride. While fluoride can be helpful with tooth decay prevention, ingesting too much can cause a painful condition called skeletal fluorosis, which impacts the bones and joints. Fluoride can leach into the well water supply from the weathering of fluoride-rich minerals with rocks and sediments. What to do if your well water is contaminated? If you think your well water is contaminated, here is a list of steps you can take to address your problem. First of all, stop using water sourced from the well. If you suspect that your well water might be contaminated due to the presence of unusual odor, strange flavors, or stains, the initial and most crucial steps is to immediately cause consuming or using the water for drinking, cooking, and other household purposes. Your health and well-being are paramount, and continuing to use potentially contaminated water could expose you and your family to various health risks. Second steps, have the well water tested to identify contaminants. After discontinuing the use of potentially contaminated well water, the next steps is to arrange for a test to identify the contaminants. Seeking the expertise of certified water testing professionals is paramount in this phase. The testing process encompasses a wide range of potential pollutants, including bacteria, chemicals, heavy metals, and more. How to treat contaminated well water? There are a few things you can do to prevent contamination of your well water. First, have your well water tested regularly to ensure that it is safe to drink. You should also keep your well maintained and sealed to prevent contaminants from entering. Next, look for the signs of well water contamination and know what to do if you suspect your water is contaminated. Finally, and the most important, is treating the water using the following methods. Ozone injection. Ozone is a powerful oxidant that is effective in killing bacteria, viruses, and other microorganisms. This treatment is often used in well water as it is an effective way to disinfect water without the use of chemicals. There are several benefits to using ozone injection in water treatment. Ozone is a natural disinfectant, so it is safe for human consumption. Additionally, it does not leave behind any harmful byproducts or chemicals. Ozone is also a very effective oxidant, so it can quickly break down organic matter and other contaminants. Backwash water filter system. A backwash water filter system is a type of water filtration system that cleans water by forcing it through a mesh or other type of filter. As more water is forced through the filter, the impurities become concentrated and are eventually flushed out of the system. The backwash water filter system is a great way to remove impurities from well water. This system is designed to remove sediments, iron, and other contaminants from your water supply. The backwash water filter system is easy to install and is a great way to improve the quality of your well water. pH neutralizer. If you are a regular user of well water, then you should definitely get to know about pH neutralization. Well water can be quite acidic, which can lead to a number of problems. Water is too acidic can corrode pipes, damage fixtures, and make it difficult to clean clothing. It can also make your water taste bad. pH neutralization is a process that helps to make your well water more alkaline, which can mitigate this problem. UV disinfection system. UV disinfection is a process that uses ultraviolet light to kill or disinfect microbes or as other microorganisms. UV light is a type of electromagnetic radiation that is invisible to the human eye. When this invisible light is applied to water, it kills or inactivates the microorganisms that cause disease. UV disinfection is a proven technology that has been used for over 100 years. It is a safe, effective, and economical way to disinfect well water. Use water filters. An effective way to make your well water safe is to install water filters in your home. Water filters purify water by filtering out contaminants. There are various types suitable for specific pollutions. Reserve osmosis filters, for example, are best for removing chemicals and metal contaminants. This will also remove sulfur, which makes your water stink like rotten eggs. Ion exchange filter remove hardness minerals like calcium carbonate, while activated carbon filters will effectively eliminate chlorine and other specific organic compounds. If your well water is hard, you should install a water softener. It contains raising beds that replace minerals ions in the water with sodium ions. Once calcium and magnesium are out of your water, it becomes soft and easier to use. As with water filters, there are various types of water softeners. They could be salt-based, salt-free, or magnetic. Water distillators will help you get rid of over 99% of contaminants in your water. You can bank on them to make your well water safe. Here is how they work. A boiling chamber boils your water at a very high temperature until it vaporizes. As it vaporizes, the water goes into a separate section called the condenser. metal and chemical contaminants cannot be vaporized, so they stay back in the boiling chamber where they are easily removed. The water in the condenser is converted back to a liquid state and it passes through a carbon post filter and into a clean reservoirs. The initial boiling process kills any forms of microorganisms in water. The vaporization separates chemicals and metal contaminants, and the post filter traps powerful contaminants like oleitive organic compounds. Using water distillators makes your water safe and potable. Disinfection of well. When to disinfect wells? After flooding or well damage, whenever the well cap is opened, if water testing positive for bacteria like E. coli or coliforms, and after periods of disuse or long vacations. Disinfection a well, typically via shock chlorination, involves adding a chlorine solution like unscented bleach to the well after cleaning and flushing, letting it sit for hours to kill pathogens, then running it through all pipes until the chlorine smells is gone, and finally retesting the water for safety. This process is crucial after emergencies like floods, well damage or positive bacteria test, requiring electrical safety, careful mixing and proper disposal of chlorinated water to protect septic system. Even with treatment options is placed, you should maintain the safety of the well water by covering well properly, carrying out water tests annual to ensure that there are no new contaminants in the well water, regularly inspected well and waste system for cracks or leakages. Correct such minor issues as soon as they occur. Is it possible to drink well water? The answer to this question is yes. It is possible to drink well water, but you should take some precautions. If you have a private well, it is important that you test the water regularly and make sure that it is free of bacteria and contaminants such as arsenic or lead. In any case, apply the treatment with the above steps, including reserve osmosis. Well water is a great source of drinking water. Sometimes it can be difficult to treat. Make sure you have the proper equipment and know what you are doing before attempting to make well water potable. Water is essential to life, yet not all sources can be considered drinkable. Natural processes and engineering systems can help improve water quality, while bacteria, heavy metals, and chemicals pose health threats, compromising quality. Thankfully, there are effective methods of water quality improvement and ensure safe drinking water. To maintain health, it is essential to consume only high-quality water, which can be achieved through various purification and quality improvement techniques. Please remember this, and thank you for your attention.